I kind of came into statistics backwards. I did physics in college, and then I kind of went into quant finance. And I've been working at that for quite a while until I realized that my knowledge of statistics was poor at best, and that I really should start to understand some of this a bit better. So kind of in my mid-20s, I had to start going back and reading some elementary probability books and basic stuff. And you kind of think you know it. So it's great. I understand statistics. I can calculate a mean and a standard deviation. And then someone asks you, what does that actually mean? In a very kind of basic, fundamental way. And you go, I can calculate a standard deviation. So what I found was that while I had kind of a lot of maths background, sometimes equations don't really make a lot of sense. So I understand computers, and I'd always been programming. And what I found was when I started to actually simulate stuff, I actually started to understand it a bit better. And when you actually see things happening via via simulation, to me, I just understood it much better as a result. Now, first of all, can everyone understand me? I'm not talking too fast or anything. Okay. The other thing I would like to stress is, well, this is a workshop, so I have some stuff here, but by all means, if you have questions or you want me to do something else, or there's anything like that, or you want me to go over more examples, like I'm not tied to what I have here. This was really just a guide for me. So if you have any questions or you want me to try something else or add some numbers or change things around just to see what happens, by all means, shout out. We'll give it a go. I've kind of set it up that most of these things run in no more than a minute or 30 seconds. And as any of you who've seen me talk either yesterday or this morning, I can happily fill 30 seconds of dead air. So that's no problem at all. The other question is, can everyone kind of see the code? I know it's a bit, on the projector here, it's not great. Now also, all of this is done in R. I'm not going to worry too much about the code itself, which is good because some of it's pretty crap, but at least it works. All I really care about is showing you the outputs. So if any of you are interested in the code and how I'm doing things, by all means ask me. But I'm not really going to focus on that too much today. It's really just, all of this is available online as well. It's been pushed up to my GitHub, and I'll give you the link to it at the end, if any of you want to kind of play around with this yourselves. Okay? So I'm not going to cover anything, like I said, I'm not really covering any high-end statistics today. It's really kind of the stuff you would learn in Stats and Probability 101. So let me just remind myself exactly in the order. So I'm going to do the law of large numbers, and what that is and what that means. The calculation of expected values. Bayes' rule, conditional probability, that sort of stuff. The curse of dimensionality, which is something you hear an awful lot about in machine learning. And then finally, the central limit theorem. So like, as you can see, none of this is rocket science, really. But what I have found is that there's often quite a lot of subtle points in these kind of things that are very, very useful to understand. And even if you kind of understand them, there's one thing about understanding it, and then there's another thing in actually seeing how it manifests itself with real data. So, or by real, I mean numbers and stuff I've randomly generated. Okay? So, first things first, we'll get started. Does anyone have any questions before we begin, actually? And please don't be shy. No? Okay. All right. So, the first thing I want to talk about is the law of large numbers. Now, has everyone heard of the law of large numbers? Or does anyone know what it isn't? Has anyone not heard of that and wants me to go over it quickly? I mean, I will anyway. It's just a question of how much time I spend on it. No. Sorry? Not heard. If you haven't heard of the law of large numbers, okay? It's one of the key kind of concepts. You have not? Okay. So the basic concept of the law of large numbers is that if you have like a random variable, as you take more and more samples, the average approaches the expected average. So the idea is that as you take more and more samples, statistics starts to rule. So your sample error gets smaller and smaller. And that's all it is, right? Now, there's a certain number of conditions around that, and we're going to show that now. So if you've got, for example, a random number like a normal or a uniform distribution between 1 and 10, the average is between 5 and 6, it's 5.5. And what you find is as you take more and more samples from those numbers from 1 to 10, you will find that the average converges on 5.5 over time. That's all the law of large numbers is. And that's kind of one of the keystones of statistics, because the idea is more data is better if it's all from the same data source. Okay? So how does that work? Okay, well, what I'm going to do is, I'll ignore the code, but I'll mention it briefly. What we're going to do is, this line here is sampling. So we're going to take a random normal number. So are you all familiar with the normal distribution? Like the bell curve? So it's centered on 0 and a standard deviation of 1. Okay? And what I'm going to do is, over time, I'm taking a a whole load of samples from that distribution, and what I'm going to do is successively take averages over from 1 to whatever size we get, and then we're going to see what happens to the value. So rather than, I've done it already, but sometimes it's easier to just run things live. So I'll just run that now. So you can see this n here, I'm scaling it in powers of 2 just to get the sampling. And while I run it, I'll run the other one. And then I'm just plotting it out using Ggplot for those of you who are familiar with the kind of the standard plotting package in R. And here's one I baked earlier. Oops. I'm sorry? Yeah. This might not look, it might not fill the screen though. Oh yeah, I might have to make that smaller for that. So you can see what's happening there is these are the sample size along the bottom. I've plotted it out on the log scale. And what's happening is at the very start, we've got a very noisy estimate of the underlying average. And then as we take more and more samples, we can see it starts to drop down and finally, and it kind of flatlines around 0. Okay? And the idea is, from a mathematical point of view, the more and more samples you take, the difference between this number here and 0 goes to 0. Okay? Now, one thing we could say though is that that might be just and we can do the same thing for x squared. So for x squared, we would expect for a normal distribution, x squared is the second moment. So that's the variance. So we would expect this number to converge on 1. And that's what we're seeing here as well. So we're starting off random noise. This is from the same data set. Random noise gets all messy still, all the way out to maybe about 1,000. We're starting to kind of converge on 1. And then as the sample size gets bigger and bigger, it gets closer and closer to 1. Okay? Everyone, anyone got any questions there? Not yet. Now we've done the same thing here, but now what I'm doing is showing I've taken 5 separate samples of data. And I'm calculating the average for each of those independent draws. So I'm just showing here that in this example here, it doesn't really matter where you start from, and it doesn't really matter where the noise comes from. All this is just noise, and it's just due to the random variations of what it is we've calculated over small sample size. But as we get more and more data, you can see the expectation is kind of narrowing down and focusing in on 0. No, so we have 5 separate samples here. So I drew, if you can think of the first one as a big long line of data, and we're taking chunks that are getting bigger and bigger, we're now doing it for 5 of them. I think there's 5 in here. And this will get more and more of a funnel shape as you took more and more samples. So I've only got 5 here for computational reasons, but if I took 100 or 1,000 or whatever, you would see much more of like a funnel shape as it's converging on 0. Okay? And that's all the law of large numbers is telling you. So this kind of sample, so this is why you have to be very wary of making inferences when you've got small sample size. Because when you've got small sample size, you have an awful lot of noise in the data. Right? And if any of you heard, there was a big scandal back in the 80s over power lines in the US. And they were basically saying that the large pylons that had power, that were distributing power across the continent, were causing brain cancer in areas that had these pylons on them. But when they looked at the data, they realized that these clusters of cancer outbreaks were in areas of very small population. So what happened was you had a small sample size problem. And when you adjusted for population, you found out that it was actually just purely random, and that you would expect to see these small clusters of brain cancer just purely due to random noise. And because people always think random is really well spread out, it actually isn't. If you actually take like a 2-dimensional sample of space, you will actually see these small clusters in certain areas. They don't actually get spread out. Okay? All right, so that's kind of the law of large numbers. Let's just to start off, did I put anything else at the bottom here? I don't think I did. Oh, I did the same thing for x squared. So the scale on this is a bit skewed because we have this 1 mad sample up here, where x squared goes very high. But in general, you see the same basic idea that we have this kind of, now it's constrained at the bottom because it's x squared, so there's nothing We can't have any negative values. And we see this convergence down, converging on 1. And we could do this for any probability distribution. The code is all available there. So if you wanted to do it for the uniform or the Poisson or whatever, you would get the same idea. You'll always get this kind of convergence down as the data gets. Now, assuming the data converges, right? So what happens if you don't have convergent data? Like what happens if there is no mean of a distribution? Are you all familiar with that concept? Have you ever heard of so there's some probability distributions do not have a well-defined mean in the sense that there is no average value. The question is, what does that mean? Does anyone know of an example of a probability distribution without a well-defined mean? Cauchy is the kind of the classic one. The Cauchy distribution, if you've heard of it, doesn't have any, there's no defined moments. So I think I have an example here of the Cauchy distribution. Oh, there, I'm doing it with the uniform. So you can see we're getting the exact same thing. So this is the uniform distribution between 0 and 1. Okay, and the average value of that is the midway point, 0.5. And again, we can see it's converging on the expectation. So it doesn't really matter what probability distribution you do it from. As long as there's a well-defined mean, you'll see this convergence. And then I do it for the Cauchy afterwards. Just scroll down. So that's what happens with a Cauchy. Okay? Yeah, I can probably bring it up on Wikipedia. I don't have it here. Hold on. Do I have Wi-Fi here? If I do, I'll bring it up. Hold on one sec. So the data is down here. So you can see it. The PDF is defined there. Yeah. So the Cauchy is a bit of a weird one in that it's parameterized by two values, like a lot of probability distributions are, like the mean and the standard deviation for normal, for example. But in the Cauchy distribution, the first parameter defines the midpoint, where the mode is, so it kind of looks like this. If you look at it, it's defined across 0 from minus infinity to plus infinity. But what the second parameter defines, I believe, it's the distance at half the height. It's that kind of thing that you see in engineering a lot. And as a result, it's got this very, very heavy tail. So what happens is the heavy tail screws up the statistics. So it basically means that you've always got this non-zero likelihood of having this outsized move being drawn from the distribution. And usually you see this a lot in heavy tail distributions that don't have a well-defined variance. But it's so heavy-tailed with the Cauchy that it actually messes up the mean as well. And that's kind of how the Cauchy works. So the question I always was asked, the reason why I'm showing this, I was always wondering to myself, well, if you say that the mean or the variance isn't defined, what does that actually mean? And what it basically means is that there is no convergence to a value. It's just going to bounce around a whole load of different things because you're always going to have these weird outsized values that are just going to mess up the statistics. So you can kind of see it there from that if I just go back. Cauchy. So Cauchy, Cauchy gets used in Bayesian statistics a fair bit, in Bayesian data analysis on the variance. So quite often you'll have a half Cauchy, which basically it truncates it at 0. So you define a Cauchy like 0, 1, and then you use the Cauchy as the variance component for the prior for an analysis. And it's used in a bunch of other things, I'm not sure where. That's the one I kind of know of it. And I think it's quite interesting as well, because it's one of them, the name is kind of familiar, but also it's got an undefined mean and an undefined variance, and that's kind of like the classic example. It's also, it's known as a stable distribution, in that sums of the Cauchy distribution form a Cauchy distribution, in the same way that like sums of the normal form a normal. So there's a few examples of these kind of stable distributions, they're called, in statistics that kind of have this property. Most probability distributions don't have them because something we're going to talk about a little bit later is the Central Limit Theorem. So if you've got a well-defined mean and a well-defined variance, averages always turn into normal distributions. And that's just kind of the probabilities, the mathematical properties of it. Okay? Anyone got any questions? Okay. So that's the law of large numbers. Nothing too shocking there. I would love to say that I'm teeing you up for later, but none of this will be particularly shocking. It's really just kind of going over the basics. Yeah, this is the expectation, I think, of the Cauchy squared. So you can see it's pretty much all over the place. These numbers are pretty outsized as we start adding up more and more. Okay, so far so good. All right, I'm going to move on now to expected value. And this is kind of where I started when I kind of started learning this stuff. And it's also why I prefer, I'm kind of weird in that I prefer simulation to mathematics. I know a lot of people like the kind of, you know, theoretical and tidiness of a nice mathematical equation that summarizes everything up, but I often find I don't get an awful lot of intuition from it. There is a certain amount of satisfaction from it, but I often find I either need to graph it or play with some kind of equation, running numbers through it on a computer to actually understand what's going on. But your mileage may vary on that. So what I'm going to do here is a really simple thing of I'm just sampling a d6. So I'm rolling a 6-sided dice, and I'm going to roll it up, and I'm going to see, as I take more and more samples, what's the expected value. Okay? Now you can figure this out by hand pretty easily. Does anyone know what the expected value of a 6-sided dice is? 3.5, right? So you add them all up and divide by the number of them. So you get 3.5. So what I've done there is I've taken a bunch of samples, I've added them all up, and I've calculated. So we see we have a sample error here. I'm only running about 10,000. So that's why you're seeing it's a little bit off. Okay? So that's kind of pointless. Everyone kind of knows that, and you can calculate that by hand. All right, well, let's move on to 2-sided dice. Sorry? Sorry, 2d6. Yes, I'm revealing my D&D background here from role-playing games as a kid, right? Or maybe not so much as a kid. That's a very easy way out. Yes, I still do play role-playing games. I am that much of a nerd. So 2d6, what's the expected value? Well, most of us learn this. It should be about 7, because it's twice 3.5. Okay, so we do that. Okay. That's pretty easy. We can see there's the different dice rolls. The average of the 2 dice is 7. All good. Now we're getting into kind of my D&D days. If we have 3 dice, this histogram did look better last night, but I seem to have redone it, and now it's given us a bad number. So what happens if we roll 3d6? So for anyone who ever played Dungeons and Dragons, when you're first creating a character, you get 3 6-sided dice and roll them, and they become your stats. Okay, so that was kind of the classic thing as a kid doing. What's your average value? Well, it's going to be 3 times 3.5. So that's 9 plus 1.5, so we get about 10.5 is what we'd expect. Okay? Again, I'm doing this in my head, and I'm just making sure that the computer matches what we get. Okay? And 10.5 is what we see. Okay? Okay, so why is that interesting? Well, one of the things we always used to talk about was, because you're kids, you like to have cool things to play with, which means basically you want your characters to have better stats. So one of the modification that happens in D&D is that when you're rolling up a character, you roll 4d6 and you take the 3 highest values. You drop the lowest. And it's a way of biasing things upwards. And the question always was then, how does that actually change the statistics? And I remember one guy in college could figure it out pretty quickly, and he told me what the answer was, and I never really understood it. But the great thing about simulation here is we can just simulate this really, really simply based on what we've done before. And then we can actually get all the we can figure out the quantiles, we can figure out mean, mode, any of the information we have, because we'll have a big long sample of all of these 4 d6s that we've rolled, where we've dropped the last one, and what's the value of that for a given one. Okay? Now we could do it exhaustively, roll them all out, but that takes quite a while, and I remember the guy filling 2 pages of A4 with all the different combinations. I certainly don't have the patience for that. So let's see how we do that. Now, what would we expect before we do anything? If we've got 4d6, we're dropping the lowest. Well, first of all, we're pretty confident, I would say, that the mean is going to go up a bit. But what is the distribution of outcomes going to look like? Sorry? Yeah, we would expect some kind of positive skew now, as in this. We would now expect, so if we think of it before with 3d6, we would have had some kind of nice bell curve across all the different examples, which I think we saw here. That's a particularly poor. Let me do that one again. With the joys of This is why we code it live. Don't do this at home, kids. We're going to make it 16 instead of 18 because there's only 16 possible outcomes because we can't have 1 and 2. And there we get a nice, hold on. So we have a nice kind of symmetric distribution centered around 10.5. So this is a nice skew. This is with the 3d6. So we have a nice bell curve that we would get centered around the mean, which is 10.5 roughly. Okay? Now, so what are we expecting? Well, if we're rolling 4 dice and dropping the bottom, there's a very low chance of getting a 3 because we would have to get 4 1s to get a 3, because anything other than, if we get 3 1s and anything else other than a 1, that answer is going to be higher than 3. So we would expect this particular part of the distribution to move down in terms of probability. And that probability mass has the area under the curve always has to be 1. If you think of it that way, it's constant. So that mass has to go somewhere. So if we're going to push it down here, it's going to get bulged up here. And in particular, what's going to happen is these higher values are going to get more pronounced, relatively speaking. There's probably going to be a small effect enough in the middle because there's already quite a bit of probability mass here. But over here, where we don't have a lot, if you think about it, getting an 18 is now going to be 4 times more likely because we don't need 3 6s, we need 3 6s and 1 other number. So we've actually got 6 chances instead of 1. Now it's 6 out of 6 to the power of 4 instead of 1 out of 3 to the power of, 6 to the power of 3. But we would still expect that to be a relatively high bump in probability. Okay? Let's see how that works. And here's one I prepared earlier. So we're seeing now we've actually got quite a skewed distribution. So there's a relatively large downweight in mass down here, and all of this has been kind of shifted sideways and bumped up. So you can see even like the counts are going to be slightly different. Oh no, the counts are going to be the same, but you can see even from that now it was, you know, quite a small rectangle, whereas now it's much bigger. So we've probably increased by a factor of 2 or 3 the chances of getting an 18. Okay? Now, as I said, trying to calculate that by hand is not trivial. I mean, you can do it brute force, and I think there is a clever way to shortcut some stuff. I remember a friend of mine doing that. But imagine doing this with 10 or 15 or 20. That's much, much easier to code up than it is to try and figure out the algebra. Especially if you're as bad as algebra I am, where trying to cancel stuff and get everything to balance, and you always make a mistake on line 3 and it screws up everything else. All that kind of, and then also in these kind of real world problems, unlike your maths professor, the numbers the correct answer isn't a nice round number, so you don't know whether you've got it right or wrong. So yeah, I just tend to code stuff because I'm much more, as bad as my coding is, it's a whole lot better than my algebra, and it's much easier to spot a mistake. So I tend to use this kind of approach, and it allows me, especially when I'm doing modeling, I start very, very simple, but I very quickly want to add wrinkles. And I find when I'm coding up these kind of, what I would call this like a generative model, where you're actually generating the data based on some further principles, this kind of approach is much easier to start adding kind of non-standard things that, you know, your equations generally to be solvable in a nice way, they tend to require quite restrictive assumptions at the start and quite like nice values. So it's the classic joke of the spherical chicken in a vacuum, if you've all heard of that joke, of the thing with an engineer. He's trying to figure out how to design a farm, and he comes up with the perfect design of a farm, but it requires spherical chickens in a vacuum for it to work properly. So, and of course in the real world we don't have that. Now sometimes a spherical chicken in a vacuum is absolutely fine for what you're trying to do, and you don't actually need, that's a perfectly fine assumption to make, because you don't really care if you're in an atmosphere or on a farm. But in a lot of cases you do care, and these assumptions can be quite misleading. And it's very hard to kind of code that up in terms of a theoretically rigorous way, whereas it's much, much easier to just code it in and then try a few different things out and stress things and change values and just see what happens. So I'm a big, big fan of kind of these kind of simulation approaches. I also like simulation a lot, for example, when I'm testing my models. And I'll build a simulation based on the outputs of the models and then compare it to the real world data. That's kind of, in the Bayesian world, it's posterior predictive checks, but you also can do it even when you're just fitting basic modeling outputs. Okay, enough pontificating. Everyone kind of follow, oh, and there's one thing I calculated, what the average is. I think it's somewhere around 12. Yeah, so we've just over 12. So we've gone from 10.5 to 12 and a bit, with a much more positive skew as well. So most of the probability mass is now in this upper area, rather than kind of evenly distributed throughout the whole thing. Okay? All right. Anyone got any questions? Nothing too groundbreaking? Yes. Okay, Bayes' rule. Conditional probability. This is always a fun one. I'm sure most of you, unfortunately, with the rise of the internet, oh, what happened? Hold on one sec. There we go, okay. Now, the rise of the internet, this probably isn't as good, but we're going to have a very quick pop quiz so far. So we have a disease in the population which has a rough prevalence of about 1 in 1,000. So 1 in 1,000 people tend to have this disease, okay? Which, as medicine goes, is actually quite low. Sorry, quite a high rate, okay? For most of these diseases, it's much, much lower than that. It'd be like 1 in 1,000,000 or 1 in 100,000 or whatever. But let's go with 1 in 1,000. We have a test for the disease, and it gives a positive result 99% of the time if the person is sick. And if the person is not sick, it gives a false alarm of 5%. So there's a person, he doesn't know whether or not he's sick or not, or he or she. They go to the clinic, they get a test, and they come back positive. So what's the probability that the person is sick? Have you all heard this problem before? And remember the answer? If you've heard the problem before and know the answer, don't shout it out just yet. For those of you who haven't heard this before, can I have a quick poll from someone? Guess, what's the probability? I'll give people half a minute to just have a think of it. So it's about 1 in 1,000 people have it. And then if you're sick, you test positive 99% of the time. And if you're not sick, you test positive 5% of the time. And someone goes in, and of course you don't know if someone is sick or not. That's why you're taking a test. So but they've tested positive. I'll just take a random poll. Anyone like to take a guess? So I don't have to pick people out? Would you like to guess? Don't worry, you won't be the only one. I've just picked on you first. Any probability at all, just have a guess. Based on the numbers. Oh. 5%. 5% chance? Okay, we have anyone else? Higher. What?
Lower, I guess.
Oh, okay.
You're sick.
Yeah, what's the chances you're sick because you've tested positive? We have 5% chance that you've tested positive. And you think it's higher? We think about... Okay. 50%? 50 more? 70%? Sorry? Okay, let's go with 70. Anyone else? Lower than 1%? Yeah. Okay. We've lower than 1%. That was a nice, real random uniform distribution here. It's great. Sorry. What do you think?
And what's the use of taking the test if the probability
That's what we are trying to understand.
Well, we'll get to that in a sec. Yeah. So what do you think? Do you think it's higher than 1%? 2%? Higher? So what do you think? Have a guess.
It should be more than 50 to be wants to take the test.
Right, okay. Okay. Now don't forget, we haven't looked at economics here. All right? I haven't said anything. What I didn't say here was a good test right? I just said a test exists out there with these parameters that look pretty good. So the person who's done it's about 2%, believe it or not. It's a little bit less than 2%, right? And what's happening here is that there is 1 in 1,000 people, right, have a 99% chance of getting it right, okay? But that means there's 999 people that have a 5% chance of getting it wrong. So when you look at the population of people who test positive, you have essentially one person will get it right. Let's just assume it's 100% accurate. That one person goes into the box of people who have tested positive, right? But then we have essentially 1,000 people, and 5% of them are testing false. So that's about 50 people. So we have about 51 people in the box of people who have tested positive, but only one of them is actually sick. So when you look at the probability, it's a little bit less than 2%. Okay? Now that took me ages to get my head around exactly why that was, because I didn't think of it in terms of splitting it into boxes. So that's why conditional probability is hard, right? And almost every time I have found that I have a really good intuition for conditional probability questions, because someone asks me them, you know it's a trick question, you go with your gut answer and say the opposite, right? Yeah, and that has actually proved far more accurate than any level of statistic knowledge I've ever gone with, because just weird stuff. The other good one is you pull a card out of a bag, and there's 3 cards in the bag. There's one card has white on both sides, one card has black on both sides, and one card has white and black on a side. And you take the card out and you put it on the table, and it's white. And then what's the probability of pulling another white card out of the bag, kind of thing. And I can't remember exactly how it works, but the answer is not what you think it is, unless you're really good at conditional probability. There's one person I ever knew who got that answer right. I wish I had it here for me. And it's all playing, because what happens is what you know and what you don't know affects conditional probability, and that can be often hard to get your head around. The other example is the Monty Hall problem. Have you heard of the Monty Hall problem? The 3 doors with the goat and the cars? Yeah. And there was a female statistics person used to ask, there was a column in one of the famous US publications, Ask Susan or something, and she got asked that about, because it was a famous game show in the 60s, and she got an absolute stream of vitriol for getting the right answer, which is, the answer is you should always, so the idea is you've got 3 doors, you choose one, and the game show host knows where the car is, and he always gives you he opens one of the doors and allows you to switch. Your optimum thing is to always to switch, because you have a 2 in 3 chance as opposed to a 1 in 3 chance. And that took me ages to get my head around. The way I always think of it is, you have a 1 in 3 chance at the start of getting it right, and you always have a 1 in 3 chance. That never changes. So if you get the option to do something else, you should take it, because then you have a better chance. And that's kind of the way I always think of that. But anyway, the key to all this is conditional probability is hard, especially if you have to start thinking about it. Right? Whereas it's hard to argue with numbers in front of you when you've simulated it. So that's what we're going to do here. So we can calculate that, as I said, analytically. It's about 1.8, I think, % chance. And you can do that like with the method I described, where you take like 0.9s and the fractions. But what we're going to do is just do it brute force. We're going to simulate a whole bunch of people. We're going to make 1 in 1,000 of them sick. We're then going to have all those people take the test, and we'll give them a chance of testing positive of 99% if they're sick, and testing positive 5% if they're not sick. And then we're just going to look at the proportion of people who are sick against the proportion of people who tested positive. And that's going to give us our conditional probability. Okay? So I'm going to talk a little bit, I'll talk a little bit about the code for this one, just so you can see kind of what's making sense. Don't worry too much about the code itself. I'm just going to go through the logic. So what I've done is I'm just creating a table of data here, right? And I'm sampling with the probability of the base rate, which is 1 in 1,000, of whether they're sick or false or not. So if they're sick, it'll be true. And if they're not sick, it'll be false, and that will be sick person, right? We then split that population into 2 groups, sick and not sick, because we know we're omniscient right now. We know exactly what's going on. So we have sick people have the true rate, so they get this number. And if you're not sick, you get true at this false rate, 5%. So we now have like a sick and not sick. The sick people have a sick person of all true, and then a bunch of trues and falses for their test result. And then the same thing for the not sick people. They have a false in sick person, and then a whole list of true and false for whether or not they tested positive. And then at the end, we're just going to stick them together and then calculate a bunch of numbers on that. Okay? So first of all, we're going to do is how many people are not sick. Sorry, how many people are sick? Right? So we have... Yeah, what? This is why you don't do things live, folks. Hang on, why is that? That should be 1,000. Oh, sorry, you're right. Yes, I have 10 million. So there's about 1,000 people sick, give or take, right? So that's 1,000 over 10 million, which is about 1 in 1,000. Okay? Sorry, oh, in a million. Yeah. Yeah, so it's a million. So it's 1,000 people over a million, which is 0.001. So we have the rough incidence rate in the overall population. Okay? Now, how many people test positive? Well, this is immediately where we get the warning signs. We've 50,000 people have tested positive. Okay? Actually more, 51,000 people have tested positive. Oh. This happened again. Hold on. There, we're back, okay. So even now, with a rough envelope, back of the envelope calculation, if you're sick and you've tested true, we can already see this is, I mean, it's not going to be exact because we've got to compare the two exactly. But already warning bells are going to start firing. So when we calculate the one over the other and combine the two together, so we have the test result is true. So we're only looking at those people. We're adding up how many people are actually sick and dividing them by the total number of people. So the proportion is just under 2%. It's about 1.9, which I think the real answer when you do the maths is about 1.87. So we're getting fairly close there. And going back to what we did at the start with the law of large numbers, as that number gets bigger, if we did 10 million or 100 million or whatever, this number would converge on the true probability. Okay? How are we doing for time? Okay. All right.
But 51 who were
Just tested positive, regardless of whether they were sick or not. So we had this number of people actually tested positive. So we can see, even though we only had 1,000 people that were actually sick, 51,000 of them tested positive, right? So, like you said, why would you give someone to take a test? So, well, I mean, that's why now there's a bunch of things. There's a bunch of medical implications on this. In like, if a test is, if you need to actually do a test, and imagine this wasn't 1 in 1,000. It's 1 in 10,000, or 1 in a million, or 1 in 100,000, which is a lot more common for what you would consider a rare disease, where you take these tests. These statistics are going to get smaller and smaller. Right? That's not getting better. This is why a lot of machine learning algorithms have problems with low base rates. So, for example, fraud detection. I don't really know of any example of fully automated fraud detection that work on probabilistic methods. You have a lot of them that work on credit card fraud, but it's largely rules-based. So I don't know if it's still true, but one of the best ways to get your credit card cancelled in the US was to buy 2 pairs of trainers and fill up a car. Sorry, the other way around. Buy 1 pair of trainers and fill up 2 cars with petrol. Because what would happen is people would steal credit cards, they'd immediately fill up their car with gas, they'd fill up their mate's car with gas, and they'd buy some expensive trainers. And almost immediately, a couple of people tried it, and it worked every time. Almost immediately, their credit card stopped working. Right, so you have these... Sorry?
It's like reverse engineering.
Yeah, they just figured, oh, you know what, I'll see if this is still the case. Oh, yeah, it is, yeah, okay. Yeah, that was me. Please reactivate the card. My credit card wasn't stolen. So, yeah, but they're all rules-based. When you're actually trying to do this probabilistically, which would be much more powerful because it's harder to game, right? So, I mean, I think now, the funny thing is, I find it quite funny that actually worked for quite a long time. You would think people would learn, but it looks like just because you're a criminal doesn't mean you're smart. So and I think this went on for quite a while. Now, whether that's still a rule that is in place, probably is, because people probably still try it. Now, if you do it from a probability point of view, though, if you're actually doing online fraud detection, for example, for a credit card company, and you're trying to detect what transactions are fraudulent, well, the incidence rate there is something like 1 in a million, right? Or maybe less. right? Just all the global transactions going around the world at any one point in time. Very few of them are actually fraudulent. So trying to detect them, any system that you've got, you really, really have to work on your false positives. And that's very, very difficult to do. Okay, so that's why a lot of these automated machine learning algorithms that do this kind of stuff don't work very well because of this. So you have the oversampling and undersampling and all these methods that people try to get around it. I'm still not convinced they'll work yet. Hopefully with the advances in things like deep learning and stuff where we can fit incredibly complex models on very large data sets, they might work, but it would be largely about getting this false alarm rate down, because that's what's killing us here. What we really need this false alarm rate down is way less than 1%, so that when you're looking at the box of sick versus not sick, there's an awful lot of people in here, so you really don't want to be taking many people out of this not sick box, so that when you do actually get over there and you're trying to figure out whether the person is actually sick, you just don't want very many people. You don't want a lot of false positives in there. Yes. So I mean, yeah. So well, that brings on what I was going to say is I'm not saying that machine learning is useless for this stuff. I don't think it works very well in a fully automated setting. What you tend to need to do is you use it as a triage mechanism. So what we've seen good examples of is in like fraud, claim fraud for insurance. We have a friend of ours. He didn't really he tried all this stuff, and for these reasons, none of them really worked. So what he ended up doing was creating like a hot or not of claims. And he just had like a ranked series of claims that would be the most likely to be fraudulent. And then you hand it over to the humans, who are very good at finding the signal from the noise. And they'll look at it. And some of the things they'll probably be able to knock off straight away going, yeah, I know that actually looks fraudulent, but you kind of see this every so often. It's probably okay. So I'm not going to bother investigating that yet. And I look at these ones and like, oh yeah, they're probably worth looking into. And that kind of stuff tends to work very well. So it can be used that way as like essentially as a labor saving exercise rather than fully automated. Now, so how does this depend on the false alarm rate? So that's one of the things we've done. So I've created a bunch of code here. So what we're doing is we're going to keep everything else the same. We're going to keep the base rate at 1 in 1,000 and the true rate at 99%. And we're going to vary the false alarm rate. And we're going to see what is the true proportion. We'll just make a plot of the true proportion as a function of the false alarm rate. So you can see as the false alarm rate is very low, our output probability is reasonably high, although still not great. It's still only 20 or 30% chance, right? Even when we're right down here, down at, let's say, 1 in 1,000, matching the incidence rate. Okay? And then as we get up and move on, you can see it basically drops like a stone. So even at a false alarm rate of about, what, say 1%, you have a less than 10% chance of finding a sick person from testing positive. Okay? And then as it goes down, it's noisy here because we did it by simulation. If you did this and used the formula, you would get a nice decaying curve. Okay? And it's trailing off and slowly, basically it starts to approach zero as your false alarm rate gets higher. Okay? And that's all just done, you can play with that. And one interesting thing, I didn't really do it here, was playing around with the base rate versus the false alarm rate versus the true detection rate, and just seeing how they interact with one another, creating a little function and plotting these out, and you can see. And generally what happens is, as long as your base rate is quite low, it's the false alarm rate that has the biggest effect. Right? So there's no point in making your thing 99.9% better or just getting closer and closer to 1. That's not really going to do a whole lot for you, because the problem is over on the false positive side. Okay? All right, anyone got any questions? All right, so what can we do about it? Well, one thing we can do from a medical point of view is maybe take 2 tests. So let's say we take 2 tests, right? And then we only declare a person sick if they're both true. Okay? Well, what does that do? So I'm just going to plot them here. So this is now a plot of taking 2 tests together, and what's the probability of the person being sick if they test positive on both as a function? And we're assuming here it's the same statistics in the test, right? So same 99 and 5, right? So you can see this now performs an awful lot better because we've got another layer of filters in. We're not going to have quite so many false alarms. We've got more stringent requirements. So therefore that improves things. And you can see comparing it to just the single test, it's much better. But can anyone tell me a potential problem with this? Sorry? No. No. Something a bit more fundamental.
False negatives will also rise.
Sorry?
False negatives will also rise.
You will get, yes, well, we're going to have false negatives anyway, but that's not that much of a problem because the false negatives are all going to be relatively low because we have a 99% chance of catching them. Yeah? So we haven't really looked at false negatives yet. Okay, I'm purely thinking in terms of... I'm assuming here both are being done. There's a more fundamental like sampling problem here. So what I'm suggesting we do is, let's say it's a blood test. You take a blood test and you test it twice, right? They might be the same test, right? So we're assuming here that these two tests are fully independent of one another, right? And that way we can combine them. But in reality, when you take a medical test, there's a good chance the results are correlated. So if you take a test once, it's like finding something in your genetic code or whatever, or something in your blood type. So therefore, when you take a second test, you're going to find it the same thing again. Now, that will control for things like random chance due to like sampling in the lab or all that kind of stuff, because those can be considered independent of the blood sample or the tissue sample or whatever. But if you're looking at something that's within the genetic, like the human medical issue, then what's going to happen is your curve is going to be somewhere between here and here, depending on how much correlation there is between the two tests. Okay? So you're going to end up being somewhere. So ideally what you would like to do is have a second test that was independent, that was looking for something else. So take a blood sample and a tissue sample, let's say. And even then, if they have the same statistics, at least then you can say, well, these two are independent of one another. So if we get both of them are true, and we have a reasonable false alarm rate of, say, 2.5%, well, then if we test positive, we're somewhere up at 70% chance. Okay? But if we don't have that problem, and that's what happens a lot in statistics, is that basically people misunderstand it. There was a very famous case, especially in medicine, there was a very famous case in the UK, you might not have heard it over in this world, where basically a woman was found guilty of murdering her children. So basically she had 2 cot deaths, and the kids were about a year apart in age, and a very well-respected medical doctor went on the stage, or went on trial, and was a witness for the prosecution, and he basically said the chances of this happening by random chance was actually like 1 in 3.6 million or something like that. And the jury said afterwards the main reason they convicted her was because of that probability just seemed so low that there was no way that she would have been innocent. The problem was that the cot death has like genetic markers that cause it. So what happened was, once one child died of it, it was very, very likely that the second child would die of it as well, because they were all carrying the same genetic code, or something in the environment or whatever. So in reality, what he did was he just took the chance of the cot death, which is like 1 in 6,000, and he multiplied it by, he just squared it, and he came up with the number of 3 million or whatever. But in reality, it was a square root of that. It was like 1 in 6,000, which people would not have convicted them of, because that's something that can just happen. You don't see that many cot deaths, right? So this is kind of the problem when you don't fully understand statistics. It's very, and this goes back to the panel discussion we had if any were in the audience. It's very, very easy to misinterpret models and misinterpret these numbers. Okay? All right. So I think that kind of covers conditional probability. Did I do anything else? No. Okay. On to the curse of dimensionality. Before we move on, anyone got any questions? No? Right. So how many here have heard of the curse of dimensionality? Yeah, it's a few of you. I'm going to guess that you guys do machine learning stuff. Yes, it gets mentioned a lot in machine learning. Okay? Yeah. So basically the curse of dimensionality is that as you add more and more variables, things just get further and further apart. All right? So what happens is, in machine learning, what you're trying to do, or generally in statistics, you're trying to find things that are close together. Because if things are close together, you can say they're similar in some way. And that's essentially how a lot of statistics and pattern matching and general, all these things kind of work, is that you try and find some kind of degree of similarity between things. So then when something is new comes in, and you say, oh, it's kind of close to these guys, well then it's probably similar to these guys, all right? And as you add more and more variables, these things get further and further apart. So it's much, much harder to say, well, what's close and what isn't close, because everything ends up far apart from everything else, okay? So one very good example of it is the no one is average principle. Has anyone heard of this?
No one is average.
No one is average, yeah.
It was cockpit design, right?
Yeah.
Back in the 50s and 40s.
Yeah, there was one famous one was a beauty contest in a magazine in the US where they tried to find the perfect ideal woman who was basically average in all the statistics, and in most of America they couldn't find anyone because no one is really average. So the idea is that if you start measuring people, we can do it in people because that's just one example. So if you measure someone by, say, the distance between their eyes, their nose size, their height, their width, their leg size, and you start adding, say, add 20 variables, you will find no one who is average at all those variables, all right? Because if you just think of it, how many people, like someone, okay, you'll have average height, but maybe you're a bit heavy, or maybe you're a bit thin, or maybe your eyes are a little further apart or closer together. So it gets more and more, if you think of it in terms of a filter of how many people have this particular trait from here to here, let's say, okay, that throws out some of the population, and then we add another condition, and another condition, and another, and another, and another. And it caused a lot of problems with, in the military, they were designing fighter aircraft, and when they were designing their cockpits, they basically took a whole load of measurements of all the people in the air forces, and then they designed the cockpit around the average pilot. And the problem was the average pilot didn't work for anyone. And when you're flying an experimental test craft, like the gear stick being an inch too far away to be comfortable was the difference between life and death. So what they found was when they started doing it, and this I think was across the Western world anyway, they had a whole load of fighter aircraft experimental pilots dying because they would take off, something bad would happen because, you know, it's experimental, and then they would crash and die. And fighter aircraft, even looking at from a basic kind of raw economics point of view, they're expensive to train, and they're quite rare, and that was very, very wasteful. And they realized after a while that one of the problems was the way they were designing the cockpits. So they stopped looking at this, and they instead basically, I can't remember exactly how they do it. I think they started coming up with slightly different cockpit designs based on the different models. So at least, even if it wasn't necessarily suiting anyone, at least there was some aspects of it would suit the various pilots, as opposed to being kind of awkward for almost everything. And they found that once they kind of changed that design philosophy, fatalities started to level off and went away, because like all these marginal differences make a huge thing. So we're going to talk a little bit about that, exactly like how exactly does this manifest, okay? So it manifests in a bunch of different ways, and we're going to do it in a very simple, we're just going to take a normal distribution again, centered on 0, variance of 1, that gives us a nice numbers between 0 and somewhere between, say, 3 and -3. And we're going to do that along multiple dimensions, and then we're going to look at a few different things. One of the things we're going to look at is the distance from the origin, from 0, 0. How far from the origin is it? Okay? And we're going to plot that distance as a function of time. Now this has all sorts of interesting statistical implications. So what I've done here is just a histogram of the distances. So what I've done here is, so this is a two-dimensional normal. We're just assuming completely independent. So we've taken two normal numbers as a vector, 3, 4, and so on up to 20, right? And what we've calculated is the Euclidean distance from 0 to the point, all right? Are you all familiar with that? The square root of the numbers squared and add them all up, and just calculate the distance. And what you find is, as the dimensionality goes up, that average distance, we're seeing this kind of distribution around it. It starts quite low, and it gets bigger and bigger as we add more and more dimensions. Okay? So when we get to 20 dimensions, we see the average Euclidean distance is somewhere just greater than 4, but there's actually very little less than 2. Okay? Now, what does that mean from the point of view of statistics? Well, it basically means that for any given probability distribution, points tend to lie in what's known as the typical set. Okay? And this becomes very important in various kind of statistical modeling methods, because when you want to find the typical set, that's kind of where the points tend to lie. And the problem is, if you look at the 0 point, which is the mode of all this probability, the top point that you find from a lot of optimization routines. You know, you're trying to find the maximum likelihood point, which is the point at the very top of the probability distribution. If you look at it here, that would be at 0, right? But it's not in the typical set. So quite often, when you find the optimal value of something, it's actually not typical of most of the data that you're actually analyzing it on. You've actually got something that's supposed to represent the data, but it's actually not representative of anything because it's kind of it's its own little special snowflake. Okay? And that becomes very important, for example, in Bayesian data analysis, where you're trying to sample from a posterior distribution, but you start at the center, because the center isn't a member of the typical set, and you want to try and find it. And what's happening is, all those values kind of form this shell, this hollow shell, which this is what we're seeing the radius of. And what happens is, you can't quite see it here. I guess it's manifesting slightly. That shell, as the probability distribution, as the number of dimensions gets bigger, that shell gets narrower and narrower, right? It gets smaller and smaller around this kind of expected radius. That's a function of dimensionality, and it just gets bigger. Now, so think of it in this way: if you're fitting like a linear model and you've got 20 variables, so you're trying to fit 20 parameters, that's not a particularly big model, right? If you're dealing with a lot of modern day machine learning problems, you might have thousands of features, and you're doing regularization on it, and you're doing all these kind of things to try and not overfit the data. But ultimately, you're dealing with like 1,000 parameters, and that's what you're trying to optimize over. Well, in that case, you're going to have 1,000 dimensions. It's going to be somewhere off here in like 10 or 20 in terms of Euclidean distance, and you're going to have this very narrow shell around it. And you're picking a point that's very, very far away right in the middle as your kind of optimum point that's somehow the best representation of the data. Okay? So you can see there, does everyone kind of see what this chart is representing in terms of a distance? I've just, for every data point, I just plotted from 0 to wherever the point was randomly generated. And then I just calculated that distance and did a histogram of the distance. So if you can think of this like a shell. So down here, even with 2 dimensions, there's very little at 0. Right? So it's all a little bit out from 0. And then as we get bigger and bigger and bigger, it's moving further and further away. So that's what the curse of dimensionality means. Just to give you another example, another illustration of that, is the average distance between points. So if you remember, I said before that we talked about similarity in some way, right? So what we want to say is, when we're trying to do pattern recognition, or we're trying to get some kind of statistical inference on the data we're looking at, what we want to say is, well, this point here has a bunch of things near it, and these things have a certain characteristic. These are all blue. So this point here is near all the other blue ones, so we're going to guess that this is blue, right? So to do that, though, we need some kind of distance measure. So what I've done there is I have that big table of data. I haven't done it for every data point, but I've just made this sample of distances between one given point in one row and the Euclidean distance between that and another point in the distribution, and just calculated what the average distance is between them. So what's happening here is we've got a plot of, as the dimensions go up and up, here's just a sample of what the Euclidean distance is. So it starts down around 2, and as the dimensions get higher, we see this increasing kind of curve. It's curving up. I mean, it's starting to curve. It's slowing down a little bit. There's a slightly negative second derivative there, but this is unbounded. As your dimensionality gets bigger and bigger, this distance is just going to go off to infinity, right? Probably slower as time goes on because of that like small deceleration effect. But your problem is, if you're dealing with like customer data, for example, and you're trying to figure out some kind of segmentation so that you can optimize your calculation of how we're going to talk about them, or even like socioeconomic, you see it a lot with like census data that governments produce, and you're trying to come up with some kind of policy for how to interact with the electorate or just generally your citizens. You might have 500, 1,000 different columns on all that kind of stuff, and you're trying to do clustering, which is trying to find all these little points in space. That's going to get harder and harder as your feature set gets richer. As you get more and more data on people, the machine learning algorithms get harder to find this kind of cluster. Sorry? Yep. Okay. All right, so that's kind of one. And then the final thing on that is the example of all the spaces in the corners. Okay? So what does that mean? Well, it's a unit sphere and a unit cube. Okay? So we have a cube that's between 0 and 1 in all the different dimensions. And then we have a sphere, or that quarter sphere, or whatever that sphere that's in the same thing. Okay? And what we're trying to do is calculate any given points, if we're just going to randomly sample points in the unit cube, what proportion of the points are within that sphere. So what's the average distance is where it's less than 1. And as you can probably guess from looking at this, as the dimensions go up, more and more of the volume of the sphere goes to 0. So as a proportion of the volume of the cube, most of the points end up at the corners, and the sphere in the middle just gets a smaller and smaller volume. Okay? So I've done the same thing there. I've just modeled all these distances. I've done a plot of it. And then I'm plotting the proportion of volume that's occupied by the sphere relative to the cube. So it starts out with 2 dimensions. We're down to about just under 80%.
So what case is this?
So we have a cube, think of it, or a square, and we have the circle in the square. And how much of the volume or the area of the circle, what proportion of the area of the circle is the area of the square. But now let's move that into 3 dimensions, where it's a sphere and a cube, and a hypercube and a hypersphere, and so on. So as we increase the number of dimensions, what proportion of volume is in the sphere? And what's happening is it's going quickly to 0. So you see by 10, I can't remember exactly what that number is, but that's less than 1%. So less than 1% of the volume is in that unit sphere. So what happens is all the data points tend to be near the corners, just kind of, if you think it kind of geometrically. And yeah. So all the corners are where all the values are. You don't actually have anything in this middle sphere. Okay? And I guess that ties in with that shell idea. If you could think of like cutting a cube out of it. Yeah. Yeah. Okay?
Then what it can be also said that when increasing dimension, the sphere bounds the distance to any point in the sphere.
Yeah.
It's bounded and it's constant as you go higher dimension.
Exactly. Yeah.
With the dimension.
Right. Yeah, exactly. And then as a result, that sphere is getting smaller and smaller and smaller as a proportion.
How we are using this in real life?
Yeah. How do we curse dimensionality? Yeah. Well, that's one. I mean, that's why. So that's why there's a couple of things. One is you'll often see dimensionality reduction. So you'll see people will get like a data set with, say, 5,000 columns in it, right? Because it's like credit scores and all this kind of stuff. Most of them are actually useless, and you don't find them very, very, like, they're all correlated with one another, and there's not an awful lot of information. So what people will do is, one of the things they did initially, purely for computational reasons, did dimensionality reduction. So they found a way of saying, okay, there's 5,000 dimensions of data, but there's really only about 2,000 dimensions or 200 dimensions worth of information, and we're going to run on the 200. But what they found was not only did it actually speed up the computation, it also made the outputs better. And that's because you've got rid of all this kind of space out there. You're now working in a much smaller feature space.
How do you define whether the dimension is useless or not? For example, I'm working in bank.
Yeah.
And now we're starting to do the scoring, of statistical scoring.
Yep.
And now we have exactly that problem.
Right.
We have millions of dimensions.
Yeah.
And we're going to, now we have not statistical scoring.
Yeah.
We just, I like tall guys and let's give them the lows.
Yeah. That you'd be surprised. I've seen worse.
And now we're going to have the statistical scoring.
Yep.
Now exactly we're working on and taking the sample and
Yep.
having the dimensions.
Sure.
And we have exactly that.
Yeah.
We have millions of dimensions.
Yeah.
And we now have to pick which dimension we should use. And
Yeah.
you're telling me that, oh, this is useless.
Well, no, it's
We're
not.
grabbing all the dimensions to
Yeah.
have it.
Can we unite dimensions?
Yeah. So there's. I mean, there's a bit beyond the scope of what I'm going to talk about, but just to take a quick diversion. essentially what you can do is there's a whole bunch of dimensionality reduction techniques. The big one will be SVD, singular value decomposition. So essentially what you have is there a marker here? I'll take a quick diversion. Sorry, that would be off the camera. Okay. I'll tell you what. I'll explain it at the break. But if you think of it in 2 dimensions, right? If you think data that's correlated, when you do samples, what you'll get is like an oval that looks like this on the screen. And what's actually happening there is you can think of it. Okay, we've got these 2 dimensions here, but really it's 1-dimensional data. So we've most of the variation is happening on this diagonal. And then when you look at it perpendicular, you only get a small variance of values.
Yes.
So what you can say is this is 2-dimensional data, but it's really got 1 dimension. So instead of looking in these 2 directions, you look along this direction.
Okay.
And it's called PCA, or singular value decomposition. And what you can do is you can plot the variance as a function of dimensions, and the algorithm naturally picks out, it ranks them all in order of variance. So you basically do a plot of variance explained as a function of dimension, and you say, okay, well, if I've got 5,000 dimensions in my data, but if I look at the first 300, that gives me 80% of the variance. I'll try those. Now, the big problem with that, though, is that those dimensions are now a linear combination of all the other dimensions, so you kind of lose explainability in your model. But for certain things like clustering, there is certain cases where it can give you very good predictive results. So you see that a lot on Kaggle, for example. But we can talk about that a bit more afterwards if you just come up to me at the end.
Some more questions.
Yeah, no problem. But this is basically, so what's happening, the key thing I thought about this, which is very interesting, it's only 10 dimensions that you basically go to 0. Right? So essentially everything inside the unit sphere, there's nothing in there. Everything is in the different corners once you go to 10 dimensions. And that was surprising. I thought we'd need to get to like 20 or 30 or 40. But it's not. It's actually very, very quickly. I mean, by 5, you're at less than 20%. So and again, it goes to the point is you can kind of see one thing and look at the dimension and see it. It's a very different thing to actually look at charts like this, and it kind of brings it home for me. Okay? All right, I've got about 10 minutes left, so I'm just going to move on very, very quickly to the central limit theorem. Has anyone got any questions? Like I said, all of this is online for any of you who use R. If any of you don't know how to use R or have any questions, by all means, my email address and the GitHub is on this at the end. I'll show it to you shortly. And I'll hold on. So yeah, so the central limit theorem. Has everyone heard of that? Anyone not heard of the central limit theorem? You have not. That's what it's called in English. In other languages, it's probably got its own name. So the basic idea is in statistics is that for any well-behaved probability distribution, well-behaved mean a finite variance and a finite mean. If you take averages of probability distributions, the mean is distributed according to a normal distribution. And that's an approximation, but as the number of samples that go into the mean gets bigger, that approximation becomes more and more accurate. So for example, if you take, so this is what I'm showing here. So what I've done is I've taken a normal distribution here, and I'm averaging 2 of them at a time, then 3, then 4, 5, 10, 20, 30, and 50, right? And what you can see here is we're getting this kind of bell curve of the averages, okay? And it's getting narrower. So there's another part of the central limit theorem is that the mean is the underlying mean of the distribution, but the distribution of it is a normal distribution, and the variance of that normal distribution is the variance divided by the square root of n, where n is the number of samples. So it would be the square root of 2, square root of 3, square root of 4, and so on. Okay? So you can see that looks like a normal distribution, to be fair, but what I've done afterwards now is I've calculated the average and the standard deviation of those samples. So I'm just moving down here. So you can see what's happening here is this is the mean value, which is basically around 0. I mean, it's -3, but to sampling error, that's pretty much 0. And this is the standard deviation of those values. So we calculate a whole load of them, say 100,000 of them. And this is what the central limit theorem would detect. So it's the variance divided by the square root of n. Okay? And you can see they're all pretty close as well. So it's telling you basically this is an illustration of the central limit theorem for normal numbers, right? Now normal isn't particularly interesting because when we get normal, we kind of get normal back, and that's not particularly interesting. So let's try a uniform distribution instead. So we're going to go with a uniform between 0 and 1, and we're going to do the exact same thing. And we see we also get a normal distribution. So if we average 2 uniform numbers, or 3 of them, or 4, or 5, 10, 20, 30, 50, we see we're getting it, it's more and more normal, and the variance is getting smaller as well. Okay? And just to show you the numbers at the end of that, they pretty much match. Okay? Now, not quite, but close enough for sampling error. Okay? And then one more interesting one I did is the Poisson distribution. If you're familiar with that, it's on count variables. So you're assuming a rate at which events occur. So you've got this value lambda. It's just defined by one parameter, lambda, which is the rate at which events occur. So if you've got a rate of, say, 0.1, and it's, say, per day, then you would expect one event every 10 days. But if you have a rate of 10, then you would expect 10 events every day, and so on. So we have a sample from a Poisson distribution, and I've used a low value of that, because for high values of the Poisson, it basically behaves like a normal. But for low values, it's a lot more distinct. So I put that in there with the low Poisson. Now, we see we're getting kind of very weird answers here. It doesn't really look like a normal distribution for small counts, right? Until we actually get quite a few samples in there. So it's only kind of by the time we get to 50 that we're even getting close. But if you actually look at the numbers, the means and standard deviation is pretty much matching what we would expect off the central limit theorem, right? So we're getting about the rate was about 0.5, which we're seeing, and we're getting closer to it as we increase the samples, right? And the standard deviation of that is still matching what we're expecting from the central limit theorem. The problem is the variance is an awful lot higher than the mean there. So there's just it's a hugely noisy distribution for this value. Whereas for higher values of Poisson, what happens is the variance of the Poisson distribution is the same as the rate. It's only got one value. So that means the standard deviation is the square root of that. So when you've got small numbers, the standard deviation gets really, really big because it's the square root of a fraction. So it's bigger than the original number. Whereas when you get large Poisson rates, the square root is much smaller. So you kind of get these two kind of weird behaviors between a low rate Poisson and a high value Poisson. So that's why for like an awful lot of stuff where you're dealing with count data, you quite often just treat it, if it's relatively frequent data, you just treat it as a normal because that's generally close enough and will often fit the data better. But when you start dealing with low frequency data, that distribution approximation doesn't really work anymore and you have to actually deal with the Poisson. Okay? I think that's it. Is there anything? Oh, one last thing. Did I do the Cauchy? I meant to. No, I didn't. I meant to put it in here. I meant to have the Cauchy in here because the central limit theorem won't hold for the Cauchy. But I forgot to add it in there. But if you add in the Cauchy distribution, as I mentioned, it doesn't have finite mean, it doesn't have finite variance. That's one of the conditions for the central limit theorem to hold. So when you violate them, if you start running this process, you won't actually get a normal distribution. Yeah, what you get is you get another Cauchy distribution because it's a stable distribution. Okay? Now you can have slightly others like power laws. So if you've got a power law like alpha stable distributions, where you have these like long log tails, like earthquakes and stuff, when you do that, they have a finite mean depending on the scaling factor. Some of them don't have a finite variance. So the central limit theorem wouldn't hold there either. But I think they fall under the, they're all stable distributions, so they kind of convert into themselves when you take averages. That's kind of how those things work. Okay? All right, that's pretty much, and I kind of timed that actually better than I usually do. Yes? Sorry, and there's my email. It's a bit small, and this is the GitHub that has all the, hold on, I'll make this a bit bigger. Yes?
Why is the standard deviation in the second vector of the dimension very close?
Because, why is it? Because that's what the central limit theorem says. it says the sampling of the mean, right? As the number of values that you're averaging over gets bigger, right? The approximation of the normal distribution gets better and better. So that's why you're seeing the standard deviation matching these. So the standard deviation is matching, but you see for lower samples, for say the Poisson rate, right? It's not really a normal distribution, okay? Because we don't have enough samples. We need more and more samples. So this is why even at 50, you see, it's kind of skewed still. If we went up to maybe 100 or 150, we would see it would become basically a bell curve, okay? Yeah, it's always only an approximation, but it works as the number of values at a time that you're averaging gets higher, it starts to approximate it better and better, okay? Okay, that's about it. If anyone has any questions, I'm going to be around for the rest of the day. By all means, hit me up. And like I said, oh, sorry, I'll put back up because I've scrolled up. All the code, it's probably not there right now because I need to push it up onto GitHub. Are you all familiar with GitHub? Yeah. As a repo? Yeah? Okay. I put them all in there. I have basically any talks I ever give go into that repo. So there's a whole load of other stuff in there. By all means, if you have any questions about any of them, just drop me an email. I'm happy to talk about this stuff all day long. Okay, thank you very much. Thank you for your time.